Going to do a very quick lesson on two-dimensional collisions and then talk briefly about center of mass. Hopefully the last two videos that you watched were very helpful in understanding center of mass. And then we're just going to look at the definition of center of mass and a question set on center of mass. So two-dimensional collisions. Something that's really important for you to recognize is the particles do not hit head on all of the time. So momentum change is analyzed by your components. So in two-dimensional collisions, you have two particles that are going to be hitting maybe in a at an angle, or maybe you even have the reverse of that. You have an explosion where the particles are exploding at an angle. So you have to look at your components. You need to look at your X and your Y components. And it's very important for you to realize that the linear momentum is conserved. So the momentum in your X direction is conserved and the momentum in your Y direction is conserved. Total energy is also conserved. So if I look at this question right here, it says a 5-kilogram disc originally at rest is exploded apart into 3 pieces. A 2-kilogram piece moves off at 3 meters per second in the positive X direction, and a 1-kilogram piece moves off at 4 meters per second in the negative Y direction. With what speed and in what direction does the third piece move? So we're going to draw our disc. And when we draw our disc, we know that it's a 5-kilogram disc. And we have a 2-kilogram piece moves off 3 meters per second in the positive X direction. So 2-kilogram piece moves this way. And a 1-kilogram piece moves off 4 meters per second in the negative Y direction. So we have 4 meters per second, and we have 3 meters per second. And then we have what's left. We have 2 plus 1, so we must have a 2-kilogram piece. And we can make a prediction here. We know that our direction is going to need to kind of balance out that X and that Y. So I'm going to make my prediction. I'm going to show my prediction with a dotted line that the direction is going to be kind of at a diagonal in the opposite X and the opposite Y direction. So let's look at our X direction and look at our Y direction. It's important for us to realize that the sum of the momentum in the X direction initial is equal to the sum of the momentum in the X direction final. So what is our momentum in the beginning? Well, our momentum in the X direction is going to be 0 because it's sitting still and this is an explosion. And in explosions, your initial momentum is going to be 0. Then in the end, we have, let's look at all of our components. Well, up here, we have this 2-kilogram piece moving at 3 meters per second. Okay, then we have 0 right here because there's no X direction, X motion, right? And then you have plus your 2-kilogram piece in your VX final position for that piece. Okay, so we end up getting that 6 kilograms times meters per second equals 0 plus 2 VX final. And we end up getting that V in the X final is equal to negative, because I'm going to take that 6 and bring it to the other side, negative 3 meters per second. And then you look in your Y direction. So your Y direction, we know that the sum of the momentum in the Y direction initial is equal to the sum of the momentum in the Y direction final. Okay, So when we look at that, we want to look at our different components. Well, we know we start with 0 momentum. And if we look at our 2 kilogram piece, our original 2 kilogram piece, we know that that's going to end up giving us 0, right? And then plus we have a 1 kilogram piece, and that's moving down. So I'm going to say that that is negative 4 meters per second. And then plus I have my 2 kilogram piece moving in my Vy final. So I end up having 4 kilograms times meters per second, because I just brought it to the other side already, is equal to 2 V final in our y direction. So we know that Vy final is equal to 2 meters per second. So now I can figure out what my end velocity is and what my direction is, because I use my V total squared equals Vx squared plus Vy squared, right? Because we're going to end up having our Vy going up and our Vx going this way. So our resultant is going to be that diagonal, your hypotenuse. So you end up getting your V in the end for this piece is the square root of -3 squared plus 2 squared. And I end up getting that my V is 3.6 meters per second. And then I need to know the direction. Well, the direction is going to be my opposite, which is my x. So we're going to end up having our opposite over adjacent. So tan theta equals our opposite, which is going to be 2 well, if we look at it in terms of this angle, this direction, okay, that's actually going to end up giving me -3 okay, divided by 2. So we end up getting our angle is going to be theta equals inverse tan 3 over 2, okay? Because we have our x divided by our y to give us that angle, okay? Or another way you could look at it is if you wanted to figure out what that angle was right there. So that angle right here would be opposite your y, which would be 2 over 3. So in the end, if you're looking at it from your y direction, your theta is going to end up giving you 56 degrees. So from the positive y direction, okay? So let's look at another question, okay? As shown in the top view diagrams, a pool ball. So when you're playing pool and you're looking at things in terms of hitting the ball in at an angle or something, you have a pool ball is initially rolling on a table at 4 meters per second when it collides with an identical pool ball that is initially at rest. After the collision, the first ball is rolling 3.6 meters per second at an angle of 27 degrees from its original direction. In what direction and with what speed is the second object moving? So we want to look in our x direction and we want to look in our y. Well, we know our momentum before is equal to our momentum after. So our momentum before, we have our 4 meters per second, okay, our 4 meters per second, and our m being the mass, plus 0 because you have your second one is at rest, is equal to 3.6 cosine 27, okay, because we're looking at just this angle right here. So that's cosine 27 times m plus V2 final M. Because remember, it's all identical mass. So we end up getting that our V2 final in our x direction, because this is specific to our x direction, is equal to 0.79 meters per second. Okay, and then when we look in our y direction, sum of momentum in our y initial equals the sum of momentum our y final. Okay, so then that's going to end up giving us, well, let's think. We have no momentum in our y direction plus no momentum in our y, because this ball is only moving in the x direction. And that's going to be equal to our 3.6 sine 27 times m plus v2 final y. So we end up getting v2 final y is equal to negative 1.6 meters per second. So when we figure out what that's going to look like, so we have 0.79 and we have negative 1.6. So we know that v final is the square root of both of those squared. So 0.79 squared plus 1.6 squared. Okay, and that's going to end up giving me 1.8 meters per second. And then if we want to figure out what the angle is, okay, so we're looking at this here. And if we want to figure out what that angle is, we're going to have tan theta equals 1.6 divided by 0.79. And we end up getting your theta is 64 degrees. Okay. Now, the next thing to talk about is center of mass. And like I said, I really hope that the first two videos that you watched today were really helpful. The center of mass is the point at which all of the mass of an object or system may be considered to be concentrated. The point that follows the path of the particle that would take. And so in the videos that you watch, it was really important to see that all of these laws that we've learned, all of these laws apply to the motion of, we're basically assuming the center of mass. So for example, the center of mass of an object is going to follow a parabolic motion, okay? Something like that. Or when you're looking at it in terms of momentum, it's very important for you to realize that in a collision or an explosion, the velocity of the system's center of mass will not change. So in a collision or an explosion, the velocity of the system's center of mass will not change. When we're analyzing motion, it's easier for us to analyze the center of mass rather than having to analyze the motion of every single individual particle, correct? Okay, but the most important thing for you to realize as it applies to this unit is that in a collision or an explosion, the velocity of the system's center of mass will not change. Okay, so if we look at the last two examples, okay, we look at the last two examples, and we're going to do that in a second. But looking at the center of mass, how do we figure out the center of mass? Well, we figure out the center of mass in our x, in our y, and it's the sum of the mass times the position. So the position of that mass times position, and sum all of those divided by the mass of the entire system. Okay, so divided by the total system's mass. And then that's going to end up giving me the center of mass for your x position, your y position, and your z position. Z is going to be like you're coming out of the page. Now, center of gravity. Center of gravity is the point for which the force of gravity can be considered to act. You're going to consider the center of mass and center of gravity at the same point because you're sitting in or you're analyzing a consistent gravitational field where you're at. Okay. So in this question, this is the very last in-class practice problem for this unit. It says, for the previous two questions, determine the speed of the system's center of mass after the collision or the explosion. Okay, after the collision and the explosion, or the explosion. So in the very first one, we have the velocity initial of the center of mass is equal to the velocity final center of mass. Okay. And if we think about it, you have a disk that's exploding. So therefore, the velocity of the initial and the final center of mass is going to be 0. Okay. Now in the second one, we're looking at the velocity of the center of mass. So we know velocity initial center of mass is equal to the velocity of the final center of mass. And remember, you had two different objects that had the same exact mass. One is moving and one is moving at 4 meters, or one is moving at 4 meters per second. One is not moving at all. So you have 4 meters per second. And then you have 0 meters per second. So you're going to find the difference between those because you have two identical masses. So not difference between those, but the divided by your two identical masses. So you end up getting that the velocity of the center of mass is 2 meters per second. Okay. Hopefully this was helpful for you. If not, go ahead and reach out and let me know how I can help.